In this recording, we will talk about what makes a bulb light up. Okay, to do that, I'm going to go to the simulation. Okay, I have a light bulb in a circuit. I have a battery, a resistor to control the amount of current flowing, and a light bulb and a switch. I'm going to take a voltmeter to measure the voltage across the light bulb. Of course, right now it's going to be 0 since we don't have any current flowing. And then we are going to also use what we call a non-contact ammeter to measure the current through the light bulb. And in this case, it is 0 amps since the switch is not flipped. So to get it to light up, the first thing we need to do is to complete the circuit by closing the switch. And you see here, we have light. Now, how are we going to change the amount of light? In this case, we have light for a current of 0.45 amps and a voltage of 450 volts. Now, what about if we change the voltage? You notice there, I have about 13 volts across the light bulb and much brighter light and larger current. So in this case, we increased both the current and the voltage, and due to both increases, we obtained more current, more light. Now, of course, if we built up a circuit to increase one and not the other, the same thing is going to happen. The minute we increase I or V, we are going to have more power, V times I, so more light. So the more current, the brighter the light bulb, the more voltage, the brighter the light bulb, P is equal to VI. That's the key. Now what the light bulb does, it takes the chemical potential energy from the light bulb and changes it into radiant energy at the bulb and heat energy. Now, one thing to note here, I don't need you to pay attention to the details of this equation, but the key thing here is, as the temperature of an object increases, its resistance also increases, because the resistivity is proportional to the temperature. So if we go back to a light bulb, if this element at the light bulb is going to heat up, when it's going to heat up, its resistance is going to increase. So because of that, for a light bulb, when we use V is equal to Ri, V is not going to be, this equation is correct, but it's not going to give us a constant R. For a light bulb, R is going to increase for different currents. So if I plot V versus I, I'm not going to get a straight line. I'm going to get a line with increasing slope. Okay, now what's a light bulb made up of? The basic makeup of a light bulb. Usually it's a sealed bulb, some tungsten filament or alloys, most of the time alloys based on tungsten, and electrical contacts. Now, the tungsten filament is a very thin and long wire. So we try to do both things. Try to make it long if we can, and thin. And we are going to have the current flow through that filament. Remember the equation for resistance, R rho L over A. So the smaller the A, the larger R, the bigger L, the larger R. So we are trying to make it very thin so we can have a large resistance. And then why is it made up of tungsten? Tungsten can sustain high temperatures. The does not break very easily if it is very thin and at hot temperature. So the filament is going to be the main resistance in the light bulb. Because of that resistance, that filament is going to heat up, and in producing heat, is going to emit light. Now the thing is, in that particular case, in the case of a light bulb, when the filament reaches a particular temperature where it's going to glow red, it's emitting light. However, everything that has any temperature is going to emit light. And the color of the light that's emitted is somewhat a measure of the object's temperature. What do I mean? For example, us. Our temperature is about this much, 30 degrees centigrade, 300 degrees Kelvin. We emit light in the infrared. So what our moms thought that we glow is actually correct. We emit light, except it is in the infrared. A heat lamp, for example, has a temperature of about this much, so it emits light in the dull red. A candle flame, that's the temperature, is dim orange, and so on. The hotter an object gets, the bluer the emitted light. Now, a curve that shows the wavelengths of light emitted as a function of temperature and the intensity of the light emitted is shown here. For example, something at 500 degrees Kelvin is going to emit according to this blue curve here. So the highest intensity light is going to be somewhere at around the 500 nanometers, which is the blue light. Now, for a 400 degrees Kelvin, we move towards the green light at a wavelength at about 600 nanometers, something like that. About 700 nanometers for red. Notice here, the hotter the object, the higher the intensity as well of the light emitted. Okay, this website here provides a neat simulation to show us the corresponding temperature to the corresponding color due to different temperatures. Okay, for example here, so we see the different colors, the spectrum of light. Now if we have an object that's at this temperature, you see the color here, how it looks like. Now if we go here, so this is black, this is red, and so on. It shows us the spectrum of frequencies that every object is going to emit depending on the temperature of the object. So it does not emit a single wave light frequency, it emits a spectrum, and the spectrum determines the actual color that we see. One interesting thing about light bulbs is the fact that they burn. And the question is, why would they burn? One thing that's important is the makeup of the light bulb. We have a very thin, long piece of wire that we call filament, made out of tungsten, that's going to get very, very hot. Now, whenever something comes very hot, it means that the atoms within that material are going to vibrate violently, are going to vibrate with a huge amplitude. Now, the higher the temperature, the more vibrations we are going to get, and the stronger are these vibrations. Actually, if the temperature is hot enough, some of the molecules, some of the atoms, are going to get enough energy and get ejected or come off the actual metal. Losing a few thousand here and there, it's no big deal, but over a long time, there is going to be enough atoms ejected to result in a deterioration of the filament, and it eventually breaks. Another factor that is as important is the stress, thermal stress, due to heating and cooling. Whenever you have a light bulb and you keep on changing the temperature, we have here big changes in temperature over a short time. If we have lots of them, then the stress due to the rapid changes in temperature is going to result into breaking the filament. Another thing worth noting, the higher the temperature of the filament, the brighter the light bulb. Now, to get light bulbs that are very bright, we need filaments that get really hot, which means their lifetime is going to be shorter, because higher temperature means it's going to be easier to get the atoms to come off. Halogen light bulbs try to fix this by actually collecting these atoms that are ejected and sending them back on the filament, so they are redeposited back on the filament. So halogen light bulbs try to fix that anomaly with light bulbs, that type of anomaly.